All right, so in this question here, we're missing a diagram, so I'm making some assumptions about some things, including the angle that we have. I just put 30 degrees in here. You can swap in the number that you actually have for that. And also just assuming kind of what this situation looks like based on the description in words. So we're imagining this block is going to slide across a flat frictionless surface, but then it's going to hit this ramp. It's going to start to go up the ramp, which does have friction, and then compress a spring. So we have some values given to us. Again, just watch that angle here. I also imagine this distance as being the distance up the ramp, like that angle distance. So we're going to use the work energy theorem to solve both parts of this problem. And our work energy theorem is the equation that tells us basically that our total initial energy plus any work done is equal to our total final energy. So we have this big long equation, including those different types of energies: kinetic energy, gravitational potential energy, and elastic potential energy, work done, and then the final for all of those energy types. And to solve these problems, a good place to start is very clearly identifying the initial and final states. So for part A, we're going to have a certain initial and final state, but then we'll have to switch that up a little bit to answer the second part of the problem. So in the first part, we're trying to find the speed that the block has at the point where it's reaching the spring, but the spring isn't actually compressed yet. So we're imagining the initial state as the block moving at 7 meters per second across the level surface, no friction, force there. But then the block in the final state, the block has moved some distance up the incline, but the spring is not yet compressed. We've had some friction force doing work on the block, and we're trying to find the speed. So if we go back to our equation here for the work energy theorem, we're pretty much just going to go through this and cross some things out that don't apply. So in the beginning, in the initial state, we do have kinetic energy. We know that because the block is moving. We do not have gravitational potential energy there. It hasn't moved up in height yet. We don't have elastic potential energy. Spring is not stretched to compress at this time. We do leave in the work term because we have work done by friction in this process. At the end, the block is still moving. It hasn't come to rest. So we do have final kinetic energy. We do have some final gravitational potential energy because there is a non-zero height at the end. And we do not, though, have elastic potential energy yet because the spring hasn't actually been compressed yet. So when we simplify that equation, we're left with that initial kinetic energy plus the work done by friction is equal to the final kinetic energy plus the gravitational potential energy at the end. And we're just going to like swap stuff in for each of these terms so that we can get this equation to a place where we can plug in the numbers that we have and solve for the final velocity. So for the initial kinetic energy, we have 1/2 mass times the initial velocity squared. That's going to be our 7 meters per second. For the work done by friction, we would multiply our friction force times the distance that the block travels up the ramp times the cosine of, we're going to use 180 degrees here because that angle represents the angle between the direction of motion and the friction force. So they're in exact opposite directions. So we use 180 degrees. And then for the final kinetic energy, that would be 1/2 times the mass times our final velocity squared. That's what we're going to solve for. And then for a gravitational potential energy would be mg times that final height. So there's a couple more things we're going to have to swap in expressions for. Those things being the friction force and the height. Because if they're giving us the distance up the ramp, that's not the same as the height. And we can write an expression for friction on an incline by imagining we have the friction force being the coefficient of friction times normal force. This is how we write an expression for normal force for an object on an incline. So we'll swap that in here. And in terms of the height, if we have the distance and the angle, we can write an expression for height as that distance times the sine of theta. So when we make those substitutions, 1/2 mass velocity initial squared. Our expression for friction is the coefficient of kinetic friction times mg cosine theta. So that theta is our 30 degrees. And then we have d cosine 180 on the other side. Sorry, I'm running out of space a little bit. I'm going to write that down here. We have the 1/2 mv final squared plus mg, and then our expression for height is d sine theta, and that theta is our 30 degrees. So from there, we've gotten everything in that we need to be able to rewrite our expression to solve for the final velocity. That's what we're looking for. We have the mass, we have initial velocity, we have our coefficient of friction, g is 10, where I have theta written here, that's our 30 degrees or whatever the angle actually is that's given. And we can solve that expression for v final, and we have it. So let's take a look then now at the second part. In the second part, we can keep the same initial conditions, but our final conditions are different because we are now looking to find the amount of compression of the spring. So when the block has moved a little bit further up, the spring is compressed. X is the variable that we use for the stretch or compression of the spring, so we see that there. We have a new height because it's moved further up the ramp. And we have, again, also then a new expression for height because if it's moved further up the ramp, that total distance that the block has now traveled up the ramp would be that original distance plus the distance that the spring has compressed. So that's why we have d plus x here. And our height expression is d plus x sine theta. So again, going through our work energy theorem equation, we do have that initial kinetic energy, no initial gravitational potential energy, no initial elastic potential energy. We still have work done by friction. We do not have final kinetic energy. When the spring is totally compressed, the block momentarily comes to rest. We have this and we have that. So I'm going to show you how to kind of expand that with some expressions that we have for these various quantities, and I'll leave you with an expression. So that initial kinetic energy, 1/2 mv initial squared. Again, that initial velocity is the 7 meters per second. The work done by friction, we have the friction force itself, so that would be mu, the coefficient of friction, times mg cosine theta, where that theta is the angle of our incline. So that whole expression there, remember, that is our friction force. So then we have to multiply that by the total distance traveled, so that's d plus x. And then we multiply by the cosine of 180, because friction and the displacement point in opposite directions. On the other side of that expression, we have the gravitational potential energy, so mg times the height, where our height expression is d plus x sine theta. Theta is, again, the 30 degrees that I have here, whatever your angle is, plus the equation for elastic potential energy. And we are going to, in this equation, be solving for x. We have d is the 2 meters. Our coefficient of friction we know, so we have all our information here. And we will be able to solve that equation for how far the spring has compressed when the block has come to rest, and that's going to give you your value for x.